Hey guys, today we are looking at our notes for 3.4 part 2, which is linear programming word problems. So we worked on yesterday setting up those linear programming problems, finding our feasible region, our vertices, and then finding our max and mins. Today going to be a little bit more challenging because we're going to be starting with just a verbal description of what is going on, and we have to create all of those things before still graphing, finding our vertices, finding our solutions, all that good stuff. So here is our problem. You can see our 6 steps over here to the side. That is going to be how we are handling this problem. And as always with these word problems, we're going to start off by defining what our variables are. And then from there, we've got some choices on steps 2, 3, and 4 in terms of order. We really just have to kind of be able to find what our feasible regions are, our constraints, our function operation, our function statement, to be able to start answering some of these questions. So let's start off by just taking a look at what this description is giving us. For number 1, we've got that a painter has exactly 32 units of yellow dye and 54 units of green dye. He plans on mixing as many gallons as possible of color A and color B. Each gallon of color A requires 4 units of yellow dye and 1 unit of green dye. Each gallon of color B requires 1 unit of yellow dye and 6 units of green dye. Find the maximum number of gallons that he can mix. So we've got dyes, we've got colors that we're mixing together to be able to create some different paints for this particular person. So when we're looking at this, we're trying to figure out, again, how many gallons of different paint can he make. And again, those paints are tinted with yellow and green, but they are 2 distinct colors. So for the sake of this, since we're going to be graphing as well as writing some stuff, I'm actually going to go away from what I traditionally do, which you guys know is context-specific variables, rather than just saying A is color A, like gallons of color A, and B is gallons of color B. I'm going to use X and Y. So I'm going to say X is just gallons of color A, and Y represents gallons of color B. Okay, so that's what we're trying to figure out. The X and Y value represents just how many gallons of color A and B we can create. So now we can start getting into some of these equations. So for steps 2 versus 3 and 4, you can really do these in any of the orders you want to. You could start off by writing your function statement first, or you could write your constraints and graph and find those vertices first. Really, you just need to make sure you do those 3 steps after you've defined your variables before you can find what those values are for each of those different vertices, and then decide like which one is your max or your min. So for this, I'm going to go in order just so that we are kind of keeping consistent with the step-by-step guides that I have created here. So our function statement, again, that is always f of x comma y. And it's trying to answer that final question of our description, which, like, he is trying to find the maximum number of gallons that he can mix. So we're just trying to figure out what is the highest number of gallons of color A and gallons of color B that could exist. All right, now I'm going to figure out like how we decide how many gallons of each one I could mix together based on how much dye I have. But if I just add those 2 values, color A and color B gallons, that's going to give us our total amount. So if we're trying to maximize that value, that would be our function statement, right? That's our function equation. So from here, now I can get into the individual constraints. So those, again, those are those limitations based on the information that we're given. So in our problem here, we are given a couple of different values, right? We know we have 32 units of yellow dye and 54 units of green dye. And then they give us that color A requires 4 units of yellow and a unit of green. And then color B requires 1 unit of yellow and 6 units of green dye. So those values we have to go through and figure out how they relate to each other. Now, our variables are set up so that X is measuring how much gallon or color A we are going to be creating, and how many gallons of color B we are as my Y value. So because those are our X and Y values, we're trying to figure out how many of each of those we can use. And this is where each of my 2 different dyes are going to represent a different inequality. So in this, I'm going to have one inequality written for each of my 2 different dyes. Right? If we're looking at For my yellow dye, I have 4 units is required for each gallon of color A, so 4 times X, and then I need 1 unit of yellow for color B, which was our Y value. So those two things added together, 4 for every gallon of color A plus a gallon or 1 unit for every gallon of color B, added together represents how much yellow dye tint I'm using. So I have up to 32 units of yellow dye. I can use exactly 32 units or I can use less than 32 units, but it has to be a less than or equal to because we only have 32 units in our budget, in our supply. So then similarly, if we're looking at color A requires 1 unit of green, so just regular old X, and then color B requires 6 units of green, that would be 6Y, and we've got 54 units of green dye. So those would be our 2 primary constraints. The other ones that we have here are kind of no-brainer ones that just we can't use negative units of either of the 2 dyes. So, or we don't want to produce negative units of our different gallons of paint. So we have to have X is greater than or equal to 0 and Y is greater than or equal to 0. In most instances, those are kind of automatic. Every single linear programming problem that we have will start off in just quadrant 1, just because most of the time when we're measuring X and Y values with an application, we're not going to have negative units of things, negative time, negative sales, anything like that. So those are our 4 different constraints. Now, when we're going to go through and try and find our different vertices, you can do that by graphing. You can do that just algebraically if you want to, because really we're just trying to figure out where do these top 2 graphs intersect each other. So if you wanted to, you could go through and just find my intersection either algebraically or using your graphing calculator, because if we rearrange these to put them into slope-intercept form, this top inequality is going to become y is less than or equal to negative 4x plus 32. And this other inequality becomes y is less than or equal to negative 1/6 x plus 9. So those would be my top 2 inequalities in slope-intercept form. So then you could graph the 2 of them to find where they intersect. So you'd have to have a pretty big piece of graph paper especially for that one, having a y-intercept of 32 for my top one. Or you could also graph it just using your graphing calculator, right? Graph those 2 of them, second, trace, and then intersection is number 5 to find the intersection between those 2 graphs. Okay, now I have already done that. If you want to do that on your calculator, you can. Your graph would look something similar to, I have this graph paper pulled up here that we could do also. My y-intercept is 32. This graph paper goes up to 36. So we've got 36, 35, 34, 33, 32 would be right here. And then its slope was negative 4, so down 1, 2, 3, 4 over 1. So we've got this line here. There we go. Down 1, 2, 3, 4 over 1. We're good. My other one was a y-intercept of 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And then it had a slope of negative 1/6, the down 1, right? 1, 2, 3, 4, 5, 6. We've got that point right there. There we go. And then obviously like our x is greater than or equal to 0, y is greater than or equal to 0 would be there and there, just because I've given us a graph paper that is just quadrant 1. So this would be our feasible region. And then our intersections, our 4 corners, our vertices, are going to be 0, 9, 0, 0. This is 8, 0, and then this is 6, 8. So those are our 4 vertices, our 4 corners of that feasible region. Right, you can do that by graphing. Our x and y intercepts are easy enough to find for those different graphs. That intersection out in the middle of space, that 6, 8, that one would be a little more challenging to do by hand. Obviously, you could solve it algebraically if you wanted to, but again, we've got our graphing calculators. You can put in y equals -4x plus 32 and y equals -16x plus 9 and have it find that intersection for you. Okay, so if those are my 4 coordinates, now I can go ahead and find what is our actual max value based on our equation up here of x plus y. Okay, so I'm going to test each of these points. I'm going to do this in pink. So we had 6, 8, 0, 9, 0, 8, or sorry, 8, 0, and then 0, 0. So if we just add those together, 6 plus 8 is 14, 0 plus 9 is 9, 8 plus 0 is 8, and 0 plus 0 is 0. So this option right here, creating 6 gallons of color A and 8 gallons of color B, is going to give us a total of 14 gallons that the painter has available. So that would be our maximum value. And again, the way that this is phrased, find the maximum number of gallons that he can mix, we would be able to say that he can mix 14 gallons. At minimum, you got to make sure you include your units, right? 14 what? 14 gallons would be what he is mixing. Okay. One more example we'll go through. This one for example number 2. We part of a job of a receptionist at a veterinary clinic is to schedule appointments. We have 2 different kinds of appointments that we're going to be looking at here. We know that the vet needs 20 minutes for just a routine office visit, and it takes 40 minutes for surgery. The vet can do no more than 6 surgeries per day just based on supplies. The office has 7 hours available that they are open for appointments. If an office visit costs $55 and most surgeries cost about $125, find how many office visits and surgeries should be scheduled to maximize the income the vet practice receives per day. Right, so the first sentence doesn't really tell us anything about our description, about like any kind of equations or anything. It's just kind of setting us up in terms of why are we talking about this, right? So from here, I'm going to just look at my variables, and that usually is going to stem from that last sentence. Okay, we're trying to figure out how many office visits and surgeries should we schedule in order to maximize the income for that practice. All right, so the x and y values that we're solving for, x is going to be regular standard office visits, and then I'm going to say that y is surgeries. And you can define it the other way, but that is how I'm just going to set it up, right? Those are the 2 different types of appointments that we are scheduling. Okay, so up in our initial kind of what we're trying to maximize, right? That function statement, our function comes from cost, right? We're trying to maximize how much money the practice is earning that day, and they tell us that we make $55 for every office visit and $125 for every surgery that we have scheduled. So 55x plus 125y would be our function statement, right? That's the equation that tells us how much the practice made during that day, and that's the thing we are trying to either maximize or minimize. Obviously, we run the clinic, we work at the clinic, we want to make money, so we want to maximize it. Okay, so that would be our function equation, or function statement. So now I need to start figuring out what those constraints are. So our constraints, one of them is obviously going to be time, just the number of, like the amount of time that we have available. So in our equation, we are given, or in our description, we are given that it takes 20 minutes for a office visit and 40 minutes for a surgery. That's the amount of time that the doctor is spending, or the vet is spending, would be 20 times x plus 40 times y. What we need to figure out is what is the time that we have available, right? They told us later in the problem that the vet is available for 7 hours a day. So what we have to make sure of is that our units match, because the 20 and 40 that we've got to find here are minutes. So when we put this 7 hours in here, because we have 7 hours available, we don't want to put it in as just 7, because that would be assuming that it's only 7 minutes. 7 hours is 420 minutes. Right, that's just 7 times 60. We've got 420 minutes available for appointments throughout the day. Okay, so that's our big equation. That's the big one. Right, the other things that we're given, really the only other number that we're given is this 6 here, and that 6 is how many surgeries a day the vet is able to do. So just between supplies and whatever it is, maybe that's just how fast and how many rooms they have available for surgical suites to be able to do those, but that is what we're given. So we need to make sure that our number of surgeries is less than or equal to 6. Right, so y is going to be less than or equal to 6. And then those standard ones, right? The vet can't do negative surgeries. The vet can't have negative office visits. So x is also greater than or equal to 0, and y is greater than or equal to 0. Right. So now this one, you probably also could get away without having to graph these, right? These are all of our constraints. We know in general the different shapes of them, that really you're just trying to figure out where those two funky ones intersect each other. But just for the purposes of us practicing those graphing strategies, let's go ahead and get all of these in slope-intercept form first, and then go ahead and graph them. So that would be subtracting my 20x on both sides, which would be 40y is less than or equal to negative 20x plus 420. I'll divide by 40 on both sides all the way through, and that ends up giving me y is less than or equal to negative 1/2 x plus 10.5, 10.5. So not ideal to be able to find that intersection here. So we've got 10.5 for our y-intercept, be right here. So if we're going a slope of negative 1/2, that would be down 1 over 2 or down 1/2 and over 1. So I'm going to do that little like down 1/2 over 1 reduces to negative 1/2 just to get myself on a nice coordinate point. And then I'm going down 1 over 2, down 1 over 2, down 1 over 2, all the way across to try and find where that is going to get me. So down 1 over 2 and off over here at 21, 0. So I'm going to go ahead and graph that across. There we go. My other constraints, y is less than or equal to 6, is a horizontal line at 6. X is greater than or equal to 0 is a vertical line at 0. Y is greater than or equal to 0, which is a horizontal line at 0. So we've got this as our feasible region, and our different vertices are 0, 6. Come on there, 6. This is 9, 6. We've got 21, 0, which I have written above, but I'm going to do it in green just to be consistent with my colors, and then 0, 0 as well. So we've got those 4 vertices that we're going to have to try and figure out which one maximizes our costs, which are our values, which again, we can kind of ignore the 0, 0. You're going to plug it in and make no money if you take in no appointments. That's obvious. The rest of these, we're trying to figure out which one is going to make us the most amount of money between our surgeries and our office visits. So I would expect that 9, 0 is going to be that one, because usually it's the furthest out in the middle of our space that is going to be our maximum value, but we're going to check just to make sure. So we go back to our function statement. So we had 9, 6. If we plug that into our equation, 55 times 9 plus 125 times 6 makes us $1,245 at 21, 0. That would be 55 times 21 plus 125 times 0, which is $1,155. And then 0, 6, 55 times 0 plus 125 times 6 gives me $750. And then, of course, 0, 0 makes us $0. All right, so pretty close, actually. I was surprised in how close that is. I think just because 21 is such a massive number that we end up still making more money taking in 9 office visits and 6 surgeries, which Again, this is what I was talking about before. You have to be careful with what the question is phrasing, like how it's phrasing the information they're requesting from you. They're not trying to figure out what's the maximum amount of money that our vet practice can make in a day. They want to know how many office visits and surgeries should be scheduled in order to maximize our profits. So now my answer should be 9 office visits and 6 surgeries. And that is my solution. I'm gonna make that look more like a 6 instead of a weird G. There we go. So that is my solution because that is the answer to the question of how many office visits and surgeries should we schedule to maximize the income of the vet practice per day. So that is our linear programming word problems. For some practice tonight, just 5 or 6 problems here from 31 to 41, continuing on that same section that you guys worked on yesterday, pages 133 and 134. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and let me know, and I will see you guys soon.